Lesson 14, determining the theoretical probability of an event. In today's lesson, we're going to get ourselves to the understanding of these three new concepts in terms of our definitions, and then jump into this activity in our exploration, and then practice the skill that we're learning from that activity. Now, if you're looking at lesson 14 and seeing that it's all about probability, you're going to realize that this is kind of a repeat of what we did in the investigation from investigation 1. So as we jump into these definitions, these things might sound similar, which would be helpful for getting our understanding where it needs to be. First one is sample space. Sample space is the set of all possible outcomes of an event. For example, a toss of a fair coin has two equal likely outcomes. The two possible outcomes would be heads or tails. Heads or tails is the sample space. So all of the possible outcomes is our sample space. A simple event is an event having one outcome. For example, rolling a 5 on a number cube is a simple event. You had one outcome out of what would be the possible other outcomes. And then theoretical probability, the last of our definitions for today, is an outcome found by analyzing a situation in which all outcomes are equally likely and then finding the ratio of the favorable outcomes to all possible outcomes. For example, the probability of tossing a coin and landing on heads is 1/2 or 0.5 or 50%. Today, the skill of being able to operate with fractions, decimals, and percents is going to be really, really important. Now, in investigation 1, we learned about experimental probability, where we tried to calculate probability. Here, theoretical probability, we're simply focusing on the aspect of finding the ratio of a favorable outcome, so something that it's asking us about, to the total or all of the possible outcomes. Let's jump into our exploration. In our exploration for lesson 14, it asks us to place 4 different colored marbles in a sack. I don't have that. I've got this nice little cup. We've got these colorful pieces on the inside here. We've got red, green, yellow, and blue. Now, to experiment with theoretical probability, we're going to randomly draw one of these different colors and then keep track of how many times that color occurs as our favorable outcome versus all of the other possible outcomes in here. That's going to be tallied by adding up all these tallies to the total number of tries that we had to reach inside, and then we'll be able to calculate what would be that frequency. From that frequency, we can calculate the theoretical probability, which would be in a fraction or percent form. Let's jump into it. Letter A says repeat the experiment 10 times, 20 times, 50 times, 100 times. We're just going to do it for that very first 10 overall trials, and then keep track of how this works out for us. So the first one right here is yellow. I'll go fast. Green. Without looking. Blue. Without looking. Red. Blue. Red. Blue. Red. 2 more. Blue. And green. That's total 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The frequency then is just simply the number of times that favorable outcome came to be. So red was 3 times, green was 2 times, yellow was once, and blue was 4 different times. If I'm going to turn that into a fraction, I'm going to put that over what would be the total possible outcomes. We had 3 out of 10, 2 out of 10, 1 out of 10, and 4 out of 10. To turn those into percentage then, you divide 3 divided by 10. 0.3 is a decimal, which is equal to 30%. 2 divided by 10 is 0.2. Times 100 is going to turn into 20%. 1 out of 10 is 0.1, which is equal to 10%, and 4 out of 10 is 0.4, which is equal to 40%. Again, fraction, decimal, percentage to show us what that theoretical probability is. Now, letter B says divide the number of red marbles that picked by the total number of times. Well, that's kind of what we did here. 3 out of 10, and then for each color, 2 out of 10, 1 out of 10, 4 out of 10. Letter C says generalize. What do you notice about the probabilities as the number of times you picked a marble increase? Now, here's the part that we don't have time to do in our video today, to go from 10 to 20 to 50 to 100 trials. We would hopefully see that in our small sample of experiment here, that the ratio stays relatively the same. If we did this over and over and over and over, these actually might become closer and closer and closer together in terms of their overall probability, because in theoretical probability, we have the same likelihood of one of the outcomes happening as all of the others. The factor that determines that is what these colors are on the inside here. You can see that there's quite a few green, yellow, and red still in, because blue was the highest amount that we pulled out. I had the same number of colors in this cup as I did any of the other colors, so it would have been relatively equal. As we do more trials, we would find that those probabilities actually come closer together, unless, of course, I had more of one color in than the other colors. That's our exploration. That'll help us get into the example problems today so we can apply how to do this and how to calculate this given the problems that you're going to see. In the example problems for lesson 14, we have the first one offering us the opportunity to identify sample space. Remember from our definition, sample space is the set of all possible outcomes for an event. So it's going to give you a scenario, and you have to identify what are those outcomes for that given scenario. In letter A, it says a number less than or equal to 3. If you're rolling a numbered cube, that's another name for a dice or a die, what's the likelihood of a number less than or equal to 3 being rolled? Well, you've got 1, 2, 3, 4, 5, 6 on that die, and if you're getting a number that's less than or equal to 3, the only options that you have are 1, 2, or 3. 4 is greater than, 5 is greater than, 6 is greater than. So that's your sample space, what would be the outcome for that type of scenario. B, using that same numbered cube or die, what's the likelihood of getting an odd number? Your sample space would be 1, 3, or 5 because those are the only odd numbers. Letter C, a number greater than 4, obviously you have 5 or 6. This one says less than or equal to, so 3 is included. When it says greater than, obviously it's not included because 5 and 6 would be greater than, 4 would be equal to in that case. Here's our definition for theoretical probability. It's the determining of an event, the probability of an event, based on the number of favorable outcomes over the total number of outcomes. Now, you're going to see this taken to the next level of understanding in the form of what would be a complement of an event. If you're trying to calculate one favorable outcome, that means at the same time there's something that's not happening as there is something that is happening. So a complement of an event is the set of all outcomes in an experiment that are not in a given event. For example, if heads is the desired event when tossing a coin, tails is the complement of that event. If you would add those probabilities together, the sum of those probabilities should always equal 1. And because addition and subtraction are inverses of each other, you can actually find probability by using what would be subtraction of 1 or 100% minus the probability of one of those events to find what is the opposite of that probability. Here's how we go about doing that when we're calculating theoretical probability. In example 2, it gives you a scenario with 4 green, 3 blue, and red marbles in a bag. You're going to randomly choose one of those. What are your chances of getting red marbles? So red marbles is the possible outcome. You'd have to calculate the total of those. You've got 3 red marbles versus the total altogether. 4 plus 3 is 7, plus 3 is 10, so you get 3 out of 10. Your probability for choosing red would be 3/10. Your probability for not choosing red would be the opposite of that. So you would have 4 plus 3 is 7, 7 out of 10. So you have the event and you have the complement of that event. B, what is the probability of randomly choosing a marble that is not green? So in the case of it being not green, you have to think, well, what are the other 2 outcomes? Green was 4 out of a total of 10. Not green would be 3 and 3 because you've got 3 blue and 3 red. So 3 plus 3 is 6 out of 10. Here's how they kind of show that in terms of how you'd write it out. The probability of green plus the not probability of green would equal 1. And then they change that around to be a subtraction problem. The probability of not being green would be 1 minus that probability. 1 minus 4 out of 10 is 6 out of 10. If you reduce that, it's 3/5 or 60%. In example 3, it asks you to think about probability in the form of chance. Chance, like probability, is the likelihood of an event occurring. And this might be just a change in language to say what's the probability of something happening or what are the chances of that thing happening. Here's an example. In a bucket, there are 10 balls numbered as follows. 1, 1, 2, 3, 4, 4, 4, 5, and 6, and 6. A single ball is randomly chosen from the bucket. What is the probability of drawing a ball with a number greater than 4? Is there a greater chance of drawing a number greater than 4 or a 1? Well, greater than 4 would have to include 5, 6, and 6. So you have 3 out of those 10 total. A number greater or a number that is 1 would be 1 or 2. So you got 2/10, which is 1/5. Now, chances is where you're taking a look at these probabilities and comparing them to each other and saying what is a higher likelihood or a better chance. You would compare these 3/10 to 1/5. 3/10 is going to be larger than 1/5 overall because 1/5 is equal to 2/10. So 3/10 is bigger than 2/10 in that case. Chance is just a different way of saying how probabilities work, or a different word that can be used in the form of probability. In example 4, it applies this skill of predictions with probability by putting it into what would be a real-world example, a carnival game. A carnival game, you drop the ball into the top of the device shown below. As the ball falls, it goes either left or right as it hits each peg. In total, the ball can follow 16 different paths. The ball eventually lands in one of the bins at the bottom, and you win that amount of money. One path is $0 as shown. What's the probability of winning? So at carnival games, just a warning, these are set up so that the probability of you winning is very, very, very low. That's the way in which they make money, because people say, oh, it's only $1 or $2 to play, and I got a really good chance of winning, but you actually don't have a good chance of winning. The probability is always in the favor of the carnival game itself. Here's our solution. You got total number of paths, 16. The number of paths to $2 is 2. You got 1 here and 1 here. The reason why they calculate 16 because it could bounce and go this way, bounce and go that way, bounce and go this way. So that overall adds up to 16. The 2 paths that you want to win are only 2 out of those 16 paths, so you got a 1 in 8 chance of winning. I mean, 7 out of 8 of those chances, the not probability of that event is going to be the winner in terms of whoever owns this carnival game. That's the people making money off of you playing. So a lot of times when people are gambling, the odds are always in the favor of the gambling game itself rather than in the odds of the person who's actually going about taking that type of risk. Let's take a look at our practice problems to apply what we learned in each of the 4 different examples from today. Lesson 14, practice problems. Letters A, B, and C ask us to use a number cube. Mr. Shane's got one drawn right up here. Think about it as a dice. It's got numbers 1 through 6. It says list the possible outcomes for each event. Now here's how you're practicing identifying sample space. Take a look at letter A. A number less than or equal to 4. If you think of the numbers 1, 2, 3, 4, 5, and 6, which one of those are less than or equal to 4? You would simply write in 1, 2, 3, and 4. Letter B says an even number out of 1, 2, 3, 4, 5, 6. You've got 2, 4, and 6. Those get written right in here. I like to put that comma in there in this fancy little bracket to show this is that sample space will be the favorable outcome for that event. Letter C, a number greater than 2. 1, 2, 3, 4, 5, 6. Greater than 2 means you're not going to include that number, which then would be 3, 4, 5, and 6. In letters D and E, Mr. Shane has drawn up here the scenario where it says you have 4 green, 3 blue, and 3 red marbles in a bag. Letter D says what's the probability of randomly choosing a blue marble? To calculate theoretical probability, you've got to look at your favorable outcomes. Blue is the favorable outcome that we have, and we have to then think about the total number of outcomes. So we've got favorable outcomes over the total. Let's take a look at what that would be. Blue is 1, 2, 3. That goes in our numerator. The total would be all the marbles added together. So 4 plus 3 plus 3 is a total of 10. Just to count that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 gives us 3 out of 10. Now the next step that you're going to need to master is to make sure you can turn that fraction into a decimal. 3 divided by 10 equals 0.3 or 3/10. Turn that into a fraction multiplied by, a percent multiplied by 100 is going to turn that into 30%. When we're dealing with probability, being able to work with percents, fractions, and decimals, a really easy way is to be able to use that conversion and always be able to do that. Letter E says not choosing red. We learned that probability has this thing called a complement, which is the opposite of what you actually would calculate for one of those outcomes. Here, not choosing red means you're going to calculate choosing green or blue. You don't want to choose red, so what's the probability of putting those other 2 things together? 2 ways to do it. You can add up green or blue, or you can subtract the total from what you're not trying to choose. Now I'll show you both ways. Green and blue would be simply figuring out the probability for each of those individual things and then adding them together. Green, you have 1, 2, 3, 4, so that would be 4 out of 10. Blue is 1, 2, 3, as we already calculated. 3 out of 10, if you add 4 and 3, you get 7 out of 10. That's addition and how you would calculate that theoretical probability. Doing it the other way in which you would subtract, you would take 1 as your total, because there are 10 marbles in here. If you pull all out, you would have 10 out of 10 of your total tries. To not get red, you would then subtract the probability of red. Red is 1, 2, 3, so you'd say 3 out of 10, 1 minus 3/10. If I'm going to turn that into a fraction problem with common denominators, I'm going to turn 1 into 10 out of 10, and I subtract, I would get 7 out of 10. Through addition, or subtraction, I can get the same exact answer when I'm calculating a theoretical probability or calculating the complement of that probability. Next up, the final practice problems. Practice problems, lesson 14, letter F and G. Letter F. Suppose there are 8 balls in a bucket numbered as follows: 1, 2, 3, 5, 5, 6, 7, and 7. A single ball is randomly chosen from the bucket. What is the probability of drawing a ball with a number less than 6? Do you have a greater chance of drawing a 7 or a 6? Here you've got 1, 2, 3, 5 numbers. 1, 2, 3, 4, 5 numbers that are less than 6. So that'd be 5 out of 8 as your overall probability for the first question. Do you have a greater chance of drawing a 7 or a 6? The second question asks us to compare two probabilities or to calculate the chances of each one of those. Probability of drawing a 7, you've got 2 of those. That's 2 out of 8, which is 1/4. Probability of drawing a 6 is 1 out of 8. Well, 2 out of 8 is greater than 1 out of 8, so the probability of drawing, or the chances of drawing a 7 is greater. Letter G, a 52 card deck has 4 kings in the deck. What's the probability of randomly drawing a king out of the deck? If you've ever played 52 card pickup, you know that there are 52 cards in the deck and you've got to pick those up if they're thrown on the floor. Those 4 kings are from the 4 different suits. Those 4 different suits are hearts, diamonds, clubs, and spades. If there are 4 different suits out of 52 cards, you've got 4 different sets. So you take 52 divided by 4, there's actually 13 of each card if you calculate from the ace all the way up to the king. Here you have 4 sets of 13, so that's 1 king out of 13 for that specific suit. So your probability of randomly choosing a king out of the deck is 1 out of 13 because there's 4 out of those. So 4 divided by 52 is 1 out of 13, or if you think about it, there are 13 of each card or each suit. That's 1 of those kings out of those 13 will give you the same probability for letter G.